So what did we talk about last time? We did root finding stuff. Talked about that as like kind of your most basic like algorithmic kernel for optimization. We did Newton's method. We talked about how it's really a root finding method, right? And when we use it for optimization, we have to be a little careful about, maximizing, minimizing, etc. We did, minimization, which we'll pretty much always do in here. It doesn't really matter if you minimize or maximize, right? You just slap a minus sign in front of your objective function. It's the same thing. There's just a cultural divide on this one where in control, we minimize because we're usually trying to minimize fuel or tracking error or something. And historically in reinforcement learning, you maximize a reward. Doesn't matter. It's the same thing. This, by the way, this weird kind of like dichotomy goes all the way back to the origins of the field. Like, I think Pontryagin, right? Minimum principle, maximum principle, it goes by both names. And there's been like just since the 50s, right? Since the very beginning, there's always been this kind of some people like to maximize and some people like to minimize. But as culturally, like control people tend to minimize and learning people tend to maximize for whatever that's worth. I'm a minimizer. Sorry, I'm a controls person. Then we talk a little bit about regularization, right? And how this is like really one of two key hacks that we need to make Newton's method work consistently to basically make sure it's headed downhill on a non-convex problem where you can have, weird behavior. And basically, right, it comes down to like, it's that second order sufficiency condition, right? We need the Hessian to be positive to have a minimum. And when it's negative, we'll actually end up going uphill instead of downhill. So, right, all the same stuff applies if you want to maximize instead. You're just going to do the opposite of everything, right? Okay, cool. So today we're going to continue this thread and basically talk about the main other hack that you need to make a convergent optimization algorithm based on Newton's method. That other thing is, right, at the tail end of last time, we did the regularization thing, but then we still had this overshoot problem, right? So what we're going to do first today is fix the overshoot problem with a something called a line search. And that's kind of the other key piece of the puzzle. And once you have both the regularization and the line search, you actually have a functional optimization algorithm with Newton's method that can do pretty powerful stuff. And then we're going to start getting into constraints, constrained minimization, which we'll probably spend at least like one more class on to cover everything. And that's pretty much it. Once we've got that, we can do a bunch of really awesome control stuff with that. Okay, so first order business today is line search. I should pause and say any questions about any of the stuff from last time, what we're doing? All good? Okay, so line search. So as we saw at the end of last time, we can often get a step from Newton's method, or like delta x, that that overshoots the minimum, right? And that's bad. And so we want to fix that. And it's a very straightforward hack that we use to fix this. We're going to do something called backtracking, a backtracking line search. There's lots of variations on this. There's many, many ways to do it. We're going to do the simplest one that actually works in practice. You can do fancier things if you want to. So the gist is, it's kind of what you would maybe intuitively expect. We're going to check the function, our objective, at the new iterate, right? So we're going to plug in x plus delta x into our function, check to see if it went up or down versus f of x, and we want it to go down, right? And then we're just going to backtrack, meaning we're going to shrink the size of delta x until we get a good reduction in f. And basically, the definition of good here is where all these methods kind of diverge and where there's differences. So many strategies for this. we're going to do the simplest one. So the like obvious simplest thing you might think about doing is just check for a decrease, right? You just plug in x plus delta x. If that's lower than f of x, accept the step and keep going. This is problematic because that actually can let you overshoot, right? You can imagine if I have a valley and I check here, I can step all the way over the minimum and end up over here and like end up doing like some crazy zigzag stuff, right? So we want to avoid that. And if you just naively check for a decrease, that's not good enough for totally avoiding the overshoot problem. So the simplest thing that really works, I'll say a simple and effective strategy, is called the Armijo rule. And what this is doing is, so, okay, we start with some alpha that we set to 1. That's going to be our step length. And then we're going to do the following thing. So I'll write this like pseudocode style. So we're going to check the new f at x plus, and we're going to plug the alpha in here, right? So alpha times delta x. So we're first going to check the full step, and we're going to see basically, so this would be the naive thing, right? Just see if this went down. Basically, we'll just make sure it's less than what we had before. But we're going to actually tack on a new term on here to make it a little bit more stringent. And I'll explain what this is doing in a sec. So let me write it down and I'll walk through what this all means. Okay, so and let me label these things. So the B here is like a user-defined tolerance. And then what this is doing, this whole second term is, so alpha times grad f transpose times delta x. Can anyone tell me what that is? Hmm? This is, okay, so this is the expected change in f based on a first order Taylor expansion, right? Okay, so the way to think about what this is doing is it's checking that the actual decrease in f agrees with a first order Taylor expansion to within this tolerance B. Does that make sense to everybody? So that's what I'm checking. So, you know, the intuition behind this is I'm using a Taylor expansion to compute this step, the delta x step. And then I'm going to plug it into the real nonlinear function and see what I get. And to sort of trust the step, I'm saying I want it to agree with the Taylor expansion to within some tolerance. Does that make sense to everybody? So this one, Armijo just uses a first order Taylor expansion in this check. The next fancier ones that you maybe will see are called the Wolf conditions, and those use a second order Taylor expansion in this check. And then there's fancier line searches that use a third order. They're called cubic line searches. So like basically what you're trying to do here is just make sure that the model you used in the Newton step, or in this case, a gradient step, right? The model function, which is the Taylor expansion, agrees with the real nonlinear function. Does that make sense? Okay, so that's kind of the idea. So this whole thing is then kind of this like expected reduction. I guess not the B part, right? The B's some like fudge factor tolerance, but this whole thing over here, right, is literally the expected decrease from a first order or Taylor, you know, Taylor approximation. So we're going to do this, and then basically then inside the while loop, we're going to just chop alpha down, and the usual heuristic is you chop it in half each time through the loop. You can do other things. So there's some constant c there. That c is some scalar less than 1 that's chopping the step length down, and then that's it. Make sense? So usually you chop it in half. You can do whatever you want. The other cool thing about this that is common in practice is this is very easily parallelized. So you can basically parallelize this line search check over like a dozen alphas and check them in parallel and just pick the best one, which is a common thing to do in practice too. Okay, so just to kind of summarize the kind of intuition here. We're going to make sure our Newton step agrees with the linearization of f to within some tolerance, which is the B. And typical values for those parameters would be, say, like C is usually a half. Usually we chop the step length in half. And then this B, this tolerance, could be anything from like, say, 10 to the minus 4 to like 0.1, something like that. So we're usually not super strict on that tolerance, but yeah, it's got to, technically speaking, it's got to be there. So if you set B to 1, right, that's like just checking the function value itself. It turns out that can fail because you can zigzag across and just jump over the minimum every time. That second term actually has to be there to guarantee local convergence. So you can prove that if you do this with the tolerancy thing, this fixes the overshoot problem to the extent that like you can prove that the algorithm will converge to a local minimum. Okay. Yeah.
For this, if you're already sampling like multiple times as you go through, is this going to be more performant than just like cutting up your space between 0 and delta x and just like sampling 5 points between there?
Yeah, so you can totally do that. That was kind of what I was hinting at, is you can multi-thread this and just check a bunch of alphas. That's absolutely a reasonable thing to do. The other thing that's lurking in what you just said that's interesting is that you're evaluating f at all these intermediate values, right? So why waste those? If you have those more f evals, you can actually use them to now fit a polynomial over the interval and try to actually minimize that polynomial over alpha and do something fancier too, right? So that's kind of what these cubic line searches do. As soon as you've evaluated f again, so like I already know f of x, I also know grad f of x, right? And if I evaluate f at x plus delta x, now I have two function evals and a gradient. That's enough to fit a quadratic, right? And if I do one more of those, I can fit a cubic, right? So you can start like doing fancier things, and people do that, right? So yeah, the like fanciest thing is to do what's called an exact line search, which is you get the step and you actually solve a scalar minimization problem over alpha to find the exact alpha that minimizes in that direction. That's like the most like legit thing to do, but that's expensive. So usually we're trying to, approximate and be cheap. It depends how expensive your F is to evaluate, right? Anybody else? Okay, let's do it. Yeah. That's okay. That's like what the tolerance is there for. Yeah. Makes sense. Yeah, we're not saying it strictly has to agree. We're just saying it has to like roughly be, like kind of within some very coarse tolerance, like do something sort of like what the linear approximation does. Okay, so let's try it. So this is what we did at the end of yesterday. Again, where we've got that same funky little like cubic function or whatever with the multiple local minima, right? And what we did last time was we showed that if we start kind of over here, that we end up going uphill, right, without the regularization. So there's that happening again. So then, right, we saw this and we fixed that problem with regularization. So let's go do that real quick. So yeah, so this, remember, this was where we were last time. So we did regularization. So we made it go to the right, but now it dramatically overshot the minimum. Bad. So here's the line search version. So backtracking, regularized Newton. So we do both the regularization like we had before, which is a hard requirement for getting a minimizer, right? And now we're also going to do the line search thing in here. And this is exactly what we just wrote down, right? And the beta we set to, oh yeah, so that's the regularizer from last time. C, which is how aggressively we chop the alpha down at each run through this loop, we set to a half. And then this tolerance B, we set to 0.1. Okay, so that's that. Let's go do that. I'm going to start at the exact same spot, just like last time. And remember, we shot way over here last time. Let's look with the line search. So there we go. So now it's getting a nice monotonic. Basically, this guarantees a monotonic decrease. So you can't overshoot, right? And then, yeah, it does kind of what you expect. Converges in like 3-4 iterations like we saw before, right? Okay. Any questions about this? Yeah. Yeah. Before you accept the step. So rather than just accepting the delta x, you are going to ultimately accept a scaled version of that alpha times delta x, where alpha is less than or equal to 1. And you're going to check it until it does what you want and obeys this condition, right? Oh, yeah. I think it ends up being a half the first time around. And then, so let's see, what do we want to do here? Let's have it dump out the alpha. We can look at it. Damn. Did it spit it out for me? No, that's annoying. This is buried in here. Yeah. That's what I want. Yeah, so that's a half. And then after that, it's probably going to be 1. Yeah. So the rest of the steps are 1, which is kind of typical. So like what this is doing, like usually you only backtrack when you're far from the optimum. Once you get close, you're going to basically take full steps because there the Taylor expansion is going to be good, right? Because you're close to the minimizer. Yeah. Can you be a little louder? Sorry. Yeah, so what this is doing is it's saying not only do you have to be less than f of x, you have to be less by a certain amount, and that amount is determined by the first order Taylor expansion. So it's saying like, okay, if f locally is sloped down like this, I expect to see at least, kind of grad f times delta x, kind of like amount of decrease. If I see less decrease than that, I know I stepped too far. Like, and that my first order Taylor expansion is not valid that far away. That's kind of what heuristically what it's doing, right?
And I mean, you're basically looking for like a linear region of this function. Like we saw there with that first x where it took a step back, is like that section is basically a straight.
Yeah, I mean, that's a really good way to think about it. Yeah. Technically speaking, Armijo is like the first order version of this, and you can do this with gradient descent. And actually, if you want to prove local convergence of gradient, like this really comes from doing gradient descent, actually. This Armijo thing is a gradient descent thing. And like if you're doing deterministic, like regular gradient descent, you also need this to get local convergence to work out. The stochastic thing with decaying learning rates is a different thing. So if you're doing Newton, actually, there's a slightly fancier version of this, which I kind of alluded to, called the Wolf conditions, that use a second order Taylor expansion. And that's kind of more legit what you should do in the Newton case, because you already have the second order Taylor expansion laying around. And there, again, what you're saying is, okay, I use this second order Taylor expansion to compute the step. If the actual f disagrees with that second order Taylor expansion, then I probably stepped too far, and I'm going to shrink back until the Taylor expansion and the actual thing agree. Yeah, because I don't trust myself farther out, basically.
It's almost like you're pushing the slope.
You're not pushing the slope. You're literally staying in the same direction, and you're just shrinking back towards x, right? Where basically the idea is that second order Taylor expansion is going to be, or first order in this case, it's going to be accurate within some epsilon ball around x, right? But if you go too far, then the higher order terms are going to dominate, and then no good, right? So the whole intuition here is like, I use the Taylor expansion to compute this. That Taylor expansion is valid within some radius of like where I evaluated it. I'm just going to shrink back until I'm within that radius where the Taylor expansion should be good. Yeah. It's a heuristic. Like there's no, I mean, I kind of gave you a range of what's typical. Like, basically, like it turns into a performance tuning thing. And frankly, if you're chasing that and messing with those a lot, you should probably just use a more sophisticated line search. Like I would say, roughly speaking, state of the art, like stuff for standard backtracking line searches are these cubic line searches that basically fit a cubic using all the evals that you've done along the way. Those are pretty good. And there's way fancier things. Like the most fancy kind of like state of the art ones that are used in like industrial strength solvers these days, like IPOpt, uses something called a filter line search. That's actually doing something a little bit more sophisticated. That's like a 2D search that's accounting for both the constraints and the objective and sophisticated ways. So there's very fancy versions of these things you can get into. This actually works. It might not give you the best performance at the end of the day, but like as long as you pick sane values for those, like it's gonna converge to a local minimum. And the idea is like this is basically a hack that is really for when you're far away from the optimum. Once you're close, none of it matters. It actually drops out once you're close because then the Taylor expansion works well, right? Okay. Anybody else before we move on? Yeah.
So what do you make sure like this
So the maximum thing is coming from the regularization that we did last time. The line search has nothing to do with that.
also avoid the oscillation.
How it avoids that oscillation thing. Yeah, I mean, it's pretty easy. I'll leave this to you as a like exercise. Like you can cook up examples that will oscillate badly without this. Basically, this extra term, and it's not going to guarantee that you'll never oscillate, but this extra term is kind of really what's preventing that oscillatory behavior. It's really easy. If you set b to 0 here and just do the naive check, it's pretty easy to cook up examples that oscillate back and forth forever. You can still overshoot with this, but this guarantees monotonic decrease in f, and it guarantees that you will locally converge to the optimum, which is not true with the naive version, and not true obviously in general with a no line search. Yeah. Okay. Anybody else? Yeah. It absolutely does slow down the convergence rate. There's kind of no way around that. So the intuition here is Newton's method converges quadratically, like super fast, once you're close. And the reason is essentially because that Taylor expansion is very accurate once you're close. So you're getting like almost the exact answer from the Taylor expansion once you're really close. When you're far away, the Taylor expansion is bad, and you're just not going to get like that kind of fast rate. So if you do a line search and you backtrack, you're losing your quadratic convergence rate for sure. So it drops down to like a linear convergence rate, closer to like what a gradient descent method would do. Yeah. No, it doesn't do that. This condition basically the part of the convergence theory is this condition essentially, if your function is nice, meaning it has like at least a couple of continuous derivatives, this condition has to hold. Do you know what Lipschitz means for a function? To be Lipschitz? It basically means the function's bounded in terms of its derivative, so literally if your function's this looks very similar to the Lipschitz conditions for a function, right? So essentially if your function is benign enough, as in smooth enough, this basically is guaranteed to hold for a sufficiently small step. And that's kind of the gist of how you prove that this gives you local convergence. No. This is, I think, got to be an offline thing at this point. Yeah, but yeah, we can talk about it. I mean, just go try it. If I think like, here's the code. If you think you're going to like play with it a little bit and yeah, but I'm happy to chat about it offline. Okay. Anybody else before we move on? Okay. Keep trucking. Here we go. Okay. So just kind of summary takeaways from this whole thing, right? So this basically the message is, Newton is awesome, but it has some issues. And then with these kind of two tweaks, namely regularization, right, which guarantees descent, and then the line search, which kind of fixes these overshoot problems, you've got a pretty rock solid method that you can do some really awesome stuff with. So Newton with relatively simple and cheap modifications. By the way, these things in general are called globalization strategies. And there are other ways to do it, completely other ways. Basically, with these globalization strategies is very effective. Finding local optima. Right, that's all we can hope for. The global problem is NP hard in general and sort of hopeless. The only exception to that is a convex problem. So if your problem's convex, then this always works and always gets you the global optimum, roughly speaking. Okay, cool. We ready to move on to the next thing? I'm feeling good? Okay, so now we're going to start talking about constraints, which are key for what we're going to do in here. And we're going to start with equality constraints because that's the easier case. And then we're going to get into, maybe by the end of today, but definitely next time, if not, inequality constraints. Cool. So here's kind of the prototypical problem we're going to talk about. So we're going to minimize some f of x just like before, but now we're going to have some other function. So we're going to say subject to some other function c of x being equal to 0. And to be super clear, right, this f is just like before. This is a function that eats a vector and spits out a scalar. And the scalar is the thing we're minimizing, the output of that function. And then the c, though, in general, this is a function that eats a vector and spits out another vector of a different size. And you can think about that a few different ways. One way is just a vector, and you want all the outputs to be zeroed out. Another way to think about that is it's m scalar constraints. So like each row, that guy is another constraint. Yeah.
Did you say F took in a vector?
Yeah, sorry, that didn't hit somehow in the tablet. Okay, cool. So this is what we're trying to do. So what we're going to do now is I'm going to like talk you through the first order necessary conditions for this guy. Intuitively, they make a ton of sense and they're pretty easy to draw, but the math version of it is like a little bit tortured and not intuitive. It is actually really intuitive, but it takes a little bit of a leap to get to the math. So I'll tell it to you intuitively, and then we'll get you the math version from there with some gymnastics. So first order necessary conditions. Which remember, right, that's the gradient equals 0 thing. And that's ultimately the thing we solve with Newton's method, right? We do root finding on the first order necessary conditions. So we already saw, for unconstrained version, it's just gradient equals 0. For this constrained version, it's a slightly more complicated, but what we're doing is ultimately like really intuitive. So basically, we need the gradient to be 0, but only in the free directions. Basically, this thing has some constraints. There's some directions you just can't move. So if I can't move in those directions, I obviously can't do anything about it. So I can have a non-zero gradient in those directions that I'm not allowed to move. But in the directions I'm allowed to move, in the sort of free directions or legal directions to move, I have to zero out the gradient in those directions. Does that make sense? It's like super intuitive, right? Pretty obvious. And then number 2, I need the constraint to be satisfied. So I also need c of x to equal 0. That's it. So the second one's obvious. The first one is a slight tweak to what we had before in that I don't need it to be totally 0. I only need it to be 0 in the free directions. So let me draw this and we'll like try to start getting some intuition and sort of eventually get to the math version. So we're going to draw a function. What I'm going to do is draw like basically like think about level sets of a bowl. Think like on a quadratic bowl, right? So I'm going to draw some level curves of this function. So think like, I don't know, it's 0 in the middle, and then it's going up like this, right? So I'll draw a few of those. So those are level sets of f. And let's say, in this case, we've got an f of x that's, it's in 2D and spits out a scalar, and those are some level curves. And then the c of x is going to be also, because I can't draw any higher dimensions, it's a single scalar constraint. And I'll draw like a line for that guy. So let's say my c of x looks like this. And let's say, remember, so I'm specifically going to draw the line c of x equals 0. And so what this is saying, I have to be on that line, right? And just for, our own purposes, I'm going to draw like the way to think about this it's a plane with a slope and it's crossing 0 on that line. And on one side of the line, it's above 0. On the other side of the line, below 0. That makes sense? So over here, we've got c of x positive, and down here, we've got c of x negative. Okay, and so therefore, right, if it's looking like this, on that line where it crosses 0, where's its gradient pointing? up and to the left, right? Okay, so let's draw that. So this is grad C. Okay, and then how about grad F? Grad F is, right, it's 0, the bottom's at the origin, and this is a bowl, and those are level curves, right? So on all those level curves, the gradient is pointing out, right? Radially outward, that's uphill, right? So let's draw some of those in. Importantly, what can you say about level curves and gradients? So level curves and gradients are always perpendicular to each other, right? So level curve is a line where the function's the same on the whole line, right? And the gradient is the direction of steepest increase. So those are like, by definition, almost perpendicular to each other, right? Okay, cool. So I think that's cool. Okay, so now what we're saying is, so let's think about this. Intuitively, I've got to be on that C of x equals 0 line, and I want to minimize the function on that line. Where's the minimizer? Yeah, it's basically as close as I can get on the line to the minimizer, right? So it's going to be over here. Okay, so now we're getting somewhere interesting. What can you tell me about the level curve at that point compared to the C of x line?
Its gradient is orthogonal to C of x.
Yeah, so I was going to first ask, yeah, the level curve has to be tangent, right? And similarly, by the same argument, the gradient has to be the gradients have to be parallel. The gradient of C of x and the gradient of f there have to be parallel. So literally, that's just another way of saying the gradient has to be 0 in the free direction, right? That's the same argument. Basically, the free direction is along the line. If I had any gradient component of f in that direction, then I could decrease my function, right? I'd just go in that direction. So the whole argument here is for this to work out, the gradient of C, i.e. the perpendicular to my free direction, right, has to line up with the gradient of f there, meaning I can't actually move in that gradient direction. It's an illegal direction. Does that make sense, everybody? Okay, any questions about this? It's like a subtle thing, but that's all it is. It's just like a tortured math way of writing gradient has to be 0 in the free directions. Okay, so hopefully that made some sense. So let's draw like, we'll draw this guy here. It's grad F. It's bad gradient symbol. Okay, grad F and grad C, sort of obviously. Okay, so they have to be parallel. They don't have to be the same length, right? They just have to be parallel. Okay, so now we're gonna like write that in math, in legit math. So in words, any non-zero component of grad F must be normal to the constraint. At an optimum. And equivalently, basically, we've got grad F must be parallel to grad C. Okay, so now that statement in like kind of the legit math way is the following. So what we're saying there is I have to be able to find, so this says where lambda is a scalar and has a name that we will. So this guy is a scalar that we call a Lagrange multiplier or dual variable. In this case, it's a scalar. There's a scalar for each constraint, right? Each line of C or whatever. So that's confusing. So we'll write this as, this is a Lagrange multiplier or dual variable. So the idea here is what that lambda is doing is it's just impedance matching the lengths, right? It's just a scalar in this case. So grad F, grad C, those are vectors. for this equation to be true, what it's saying is I have to be able to find some scalar lambda that can make that equation work out, right? Okay. Is that cool? Everyone clear on this one? Yeah. I'm just making it up. Like, I'm drawing a cartoon. This is the one I've decided to make up. So you have your bold, and then you've got this like C is some sloped thing, and that's the line where it's crossing 0. And I'm telling you, it's above to the left and below to the right. And like that's, yeah. So, okay, so maybe we should clarify what's going on here. So this is a plane. I'm looking down on this plane. X is 2-dimensional. So I've got like an x1 coordinate. Maybe we should write that in explicitly. So this is like x1, this is x2, right? And so f of x and c of x, like x is R2. And then the value of these guys, right? F, right? The scalar, value, f of x is sort of in this, out of the plane direction. What I'm plotting here are the level curves of those functions because I'm bad at drawing 3D things. So the way to think about this is f is some bold that's coming out at you, right? And I'm plotting its level curves. And so c is some plane that's coming out of the board up into the left and going down into the board, down to the right. Okay. Yeah, sorry about I guess I could draw you a side profile maybe, but it's I think this is like this is the best I can do drawing wise. I could do a 3D render plot, I guess, in Julia or whatever for this. Is everyone clear on that? Like what I'm trying to get at there? Yeah. Well, the gradient is by definition the direction of greatest increase. So in this particular function, that direction is up and to the left. That's what the gradient is. It's the uphill direction, right? So yeah, if I flip the sign on C, if I wrote a different C down, it would point the other way, right? Like I could put a minus sign on my function and point it the other way, sure. Okay, everybody clear? Okay. So yeah, this is a bit of a leap, right? Like this 1 and 2, I think are intuitive. Getting from 1 and 2 to that is like a little bit of gymnastics. Hopefully not too bad. Okay, so that's like the sort of the thing we just drew. And then in general, if I'm in some higher dimensional space, right, where I've got a bunch of constraints, i.e. C is vector valued, it looks like this. We would have df dx plus lambda transpose dc dx equals 0. And then lambda in that case would be in Rm, i.e. there's one lambda for each dimension of the output of C, right? Basically, if you have a bunch of scalar constraints and you stack them up in that C, there's a lambda for each one of those constraints. That's kind of the way to think about it. That should be M. Okay, cool. So that's our first order necessary condition thing. And then based on that condition, we're going to do some other, just make some stuff up. So based on this gradient condition, we're going to define this other function called the Lagrangian. That's a function of both the x, which we call the primal vector, and the lambda, which we call the dual vector, dual variables. And this thing is our original function that we're minimizing f of x plus lambda transpose c of x. So this thing basically stuffs all the stuff together. It stuffs your objective and your constraints and your Lagrange multiplier all together in this one scalar valued function. It's called the Lagrangian. And the whole reason that we do this is basically convenience. Basically, with this thing, now we've like remapped this into a nice, clean, single root finding problem. So now with this Lagrangian, we have grad x of this guy is our gradient condition that we just derived. So I can write it transpose this way. If damn it. So this is partial c partial x transpose lambda. So this guy equals 0, and then grad with respect to lambda of this guy is just the original constraint function that I need to be 0. So that's just like a slick way of packaging the whole thing together into a single root finding problem on a single function. Pretty cool. And then we just solved those two conditions, right? That's our whole thing. Those are the two things we needed. That's number 1 and number 2 from the very beginning. We just solved that whole thing with Newton. So I'll write that down for you. So we're going to Taylor expand the whole thing. So we're going to, that grad x, L, we're going to write it as like, x plus delta x, lambda plus delta lambda. And I can't write. And approximately, right, so the original gradient. And then we're going to get d squared L dx squared times delta x. And then we're going to get d squared L dx d lambda, the mixed partial times delta lambda equals 0. And then if I just think about this for a second, right, the first term's obviously like this Hessian thing. The second term, what's that second term? Looking up here, right? If I take the derivative with respect to lambda, I just get back the constraint. And I take another derivative of that with respect to x, so that's just the constraint Jacobian. So this is partial c partial x transpose. Cool. So that's the first row of our Newton thing. And then the second row is going to be grad respect to lambda, L, and we're going to do the same thing, x plus delta x, lambda plus delta lambda, and kind of Taylor expand this thing. So we're going to get out c of x plus partial c partial x times delta x. What about the lambda stuff? Any lambda stuff? What are we thinking? So if I take the derivative of Lagrange with respect to lambda, I just get the constraint function back, which only depends on x. So there's no lambda dependence in here. So just that equals 0. And I can sort of, yeah. So now that's it. This is the Taylor first order Taylor expansion of this, like, of these first order necessary conditions in terms of Lagrangian. This is what I do Newton's method on. I can stack all this stuff into a big like root finding thing, and it looks like the following. So we're going to have d squared L d x squared. We're going to have partial c partial x transpose partial c partial x, and then 0. We're going to solve for delta x, delta lambda. And then the right-hand side is going to be minus grad with respect to x of the Lagrangian, and then minus c of x. So everyone see how I got that? I just took these two things and moved stuff over to the right-hand side. Basically, right, I took this guy, moved c over to the right. I got minus c over here. The other term is here. Same thing with the top, right? Took the terms that I would think that's in the lambda and left it alone. Moved everything over the right-hand side. Make sense? Okay. So it turns out, so can anyone tell me anything about that matrix? Have you noticed anything about it? It's symmetric. Yeah, that's right. It's a symmetric matrix, and it has a really particular structure. Basically, you've got a Hessian in the top left, and then you've got constraint Jacobians, and the same thing transposed in the other blocks, and then you've got a 0 block in the lower right. So that structure is ubiquitous in optimization. Basically any constrained optimization problem, you're going to end up with a linear system that looks like that. It's so common that it has a name, and there's like specialized solvers for exactly this stuff. So this is called a KKT system. I haven't told you why that's what it's called yet, but that's what it's called. The KKT, does anyone know what that stands for? Yeah, so this is Karush-Kuhn-Tucker. People, it's a bit of an abuse to call this KKT system. The reason is, so these conditions I just wrote you down, this Lagrangian gradient equals 0 thing for inequalities, that's it. The similar conditions for the inequality case, which we're going to talk about in a minute, are called the KKT conditions, Kruskal-Tucker conditions. Just equalities, technically they're not KKT conditions, but people, for abuse of notation or whatever, still refer to them that way. Pretty much people refer to any first order necessary conditions for an optimization problem as KKT conditions, I would say in general. And so that's kind of where the name comes from. So KKT conditions are these gradient equals 0 things. KKT system is the linear system that shows up when you do Newton on that thing. And again, it's very structured. There's even more structure lurking in here that we haven't talked about yet that you can exploit to solve this problem like super fast and all that good stuff. We'll get there, but yeah, okay. So any questions about that? All right, cool. So one more thing I want to tell you about before we kind of go do this is the so-called Gauss-Newton method. Which is sort of one more little approximation that shows up a lot. So I want to go look at that top left block, that Hessian thing. So this is d squared L dx squared. And if I, look at what L is up here and think about this thing and sort of like expand this out a little bit, the first thing is going to be, it obviously has the Hessian of the objective function. That's cool. We're fine with that. But then it also has this second term, which is, I'll write it out like so. It's the derivative of this constraint term. So dc dx transpose lambda. So basically, it's another derivative of this constraint term. And it sort of involves second derivatives of the constraints. So C in general is a vector. dc dx is a matrix. Then if I take another derivative with respect to x, what do I end up with? A third rank tensor. Very annoying, expensive to compute, blah, blah, blah. So unsurprisingly, we very often just throw this term out. So let's write that. Basically, there are actually tricks to compute this efficiently, so you don't have to compute the full tensor. The reason is that it's actually multiplied by lambda in there. So the Jacobian vector, basically you can play Jacobian vector product tricks like all the auto diffing toolboxes do, right? To compute this more efficiently, if you have a sophisticated auto diffing package, you can actually compute that whole term in a more efficient way, but that's kind of hard. And naively, if you were to try to like write this down, it would be a tensor with like a weird, tensor producty thing, which is expensive. It is annoying in general, and people are scared of tensors. So generally speaking, we try to avoid this. So we're going to play around with it, and you can see for yourself. So let me just write this out. So basically, we often drop that second term. This term is often called the constraint curvature term, and that's because, right, we have the linear approximation. D squared C dx squared is the second derivative of the constraints. That's a curvature, right? So that. And if you drop that second term and just use the Hessian of the objective, then this is called Gauss-Newton. So I will say Gauss-Newton is almost standard in a lot of robotics applications. Like we do this all the time. So theoretically, you get slightly worse convergence. Than a full Newton method. But unless you're really sophisticated about implementing that computation with like fancy, Jacobian vector, tensor vector product tricks, it's pretty expensive to compute that. And often a Gauss-Newton method will win on wall clock time. So it'll pretty much always take a few more iterations than a full Newton method. But if the iterations are a lot cheaper, it can end up winning in wall clock time.
modifying these things.
Yeah, you'll still get a good decrease. It'll still work. It just takes more iterations in general. The convergence rate's slightly worse. Usually, again, like I said, if you can compute that term cheaply, cool, go for it. If it's really expensive and annoying to compute and you don't have a super fancy auto diffing toolbox that'll do it for you, and you don't want to write it by hand, just leave it out. It's probably fine. So more iterations, but iterations are cheaper. And often you win with Gauss-Newton in terms of wall clock time. Okay, questions about that? Yeah. Yeah, literally, we're just going to leave that second term out. And just instead of using the Hessian of the Lagrangian, we're just going to use the Hessian of the objective, right? So we're just using Hessian of F. We're just completely skipping that second term. Cool? Okay, so let's go do it. Here's some code. Yeah. Oh. Are we, say again? No. If the constraint's linear, the iterates will stay on it. If the constraint's nonlinear, you're approximating it, right, with a linearization. So in general, you won't stay on it, but you'll track it, you know, and this ends up being subtle. Oh, yeah. Okay, so let's do some stuff. We're going to do a slightly fancier version of what I drew with an actual nonlinear constraint instead of a, because I can do this in code better than I can draw by hand. So this is a quadratic bowl. So I'm plotting the level sets of the bowl just like before, but rather than the constraint just being a line, the constraint here is a quadratic one. It's a nonlinear constraint. So I have to lie on the yellow line. That's the yellow line is C of x equals 0. That makes sense? If you wanted to think about what that thing looks like in 3D, it's some kind of, I don't know, roughly parabolic, weird looking bowl that sort of crosses, you know, the plane on the yellow line. Okay, so we got to be on the yellow line, and then the unconstrained minimizer is over here somewhere. So intuitively, the constrained minimizer is about here on the yellow curve. Make sense? Okay, so let's see what happens. What do I want to do first here? Okay, so we're going to start with something benign. Try to make this like, start over somewhere on the left. Okay, oh, yeah, look at that. So yeah, another thing to say about this is you don't have to give it a feasible initial guess. The initial guess can be, which in general, by the way, like for us, right, equality constraints are usually going to be our dynamics of our robot in our case. So those are grotesquely nonlinear and terrible. So if I had to always give a feasible initial guess, this would be pretty bad. So this is like one of the nice things about this, right? So we'll start there. Oh, maybe let me push it over some more. Okay, yeah, cool. So I'll start over here. This is like sort of roughly feasible. We know the answer is somewhere over here-ish. Let's see. And then what we got? So here's the Newton step. It's exactly what we said. I'm going to use forward diff to get the Hessian of the Lagrangian in this case. So we'll do full up Newton. Constraint Jacobian. That's the KKT system, as we wrote down, minus grad F, or minus grad Lagrangian, minus C. This is like exactly what we just wrote, right? Should be cool. We're going to start there. And now we're going to take some steps. Okay, so that's the first step. And note that I don't have a line search implemented, right? So if I kind of overshot and maybe did some bad things, but just thinking about what this did, right? And think about like what we've asked it for, this kind of makes sense, right? So basically I started here, I'm using a linearization of the constraint. So I'm going to have to lie on that tangent line, right? This goes back to your question about, am I guaranteed to stay on the constraint? No. So I moved towards the minimizer, which is up here somewhere, on the linearized constraint. So that all checks out intuitively, right? Let's take a couple more steps and see what happens. So now I've stepped back towards the constraint. That looks pretty good. Take a couple more steps. So now I'm on the constraint and I'm pretty much where I think I should be. Yeah, and now I've converged. So very similar, behavior overall, where it's like 4 or 5 steps with a reasonable starting guess, I'll get where I want to be. That's for next time. Let's see, what else are we gonna do? Okay, so what should I do now? Let's start somewhere else. Let's start in a harder spot, farther away, and see what happens. Okay, so I'll start up here now.
What's the number of lambda?
Let's see. No, definitely not. It's going to be non-zero for sure, right? Because there's some non-zero gradient over here, right? So, right. Well, it's not a slack. It's a different thing. It's a multiplier. But there's going to be a non-zero gradient of f here because the minimizer's over here, right? So intuitively, that gradient is pointing in this direction. Right? So like, which lines up with grad c here. But that lambda is basically doing impedance matching between grad c and grad f at that spot, so that they have the same length, so that they cancel each other, right? That's what it's doing. So it's definitely non-zero. We can like spit it out here and see. It says, so this is the whole, oh, this is weird. I think that got cleared out somehow. Because it should have like a whole vector of stuff in it. So I don't know. Go look at the code. I don't want to do too much unscripted live coding. This is risky. Okay, so that's that. Let's start somewhere else. So we're going to start up here this time. What do we think is going to happen? It should probably like roughly track the constraint and kind of move around. That's what we want to happen, right? So that seems reasonable. So we linearize the constraint, try to minimize along that line, end up here. Let's see what happens next. Ooh, what happened now? Let's see, let's take, that seems reasonable. Sort of reasonable. What are we doing? Okay, so but we ended up, so we went down here, that all seemed fine. Then we shot back this way. And we're kind of ending up stuck over here. What's up with that? Yeah, so the algorithm's stuck. We're stuck, we're stuck like it looks like right around here somewhere. Not only is it stuck at a not, any kind of local optimum, it's actually stuck in an infeasible spot that's not even on the constraint. That seems bad. That's definitely not what we want. Anyone have any thoughts on what the hell's going on here? Definitely not overshooting, right? It's basically not moving. I'm not doing a line search here, which I should be doing in general, but it's actually stuck in this random spot and the steps are coming back 0. I think that's actually not the case here. There's those things aren't quite lined up either. There's some weird stuff happening and I'm kind of like maybe oscillating around just in this weird little spot over here. There's some serious badness happening.
Is it because the gradients are about already?
Well, the gradient of the constraint here is like something like this, right?
Yeah.
And if I were to draw like what the gradient of the objective is, it's maybe, I don't think they're perfectly lined up here. Good check. Okay, so that's bad. So let's try the Gauss-Newton thing real quick, just for fun. Or maybe should I do this first? Maybe I'll do this first. Okay, so this is our Hessian, right? That seems questionable. So, well, so what is this here? This is the Hessian of the Lagrangian, right? So the Hessian of the objective is just this del squared f, right? So let's look at this guy. So this is an important point. Okay, so Hessian of the objective alone, this is nice, right? So remember, we want this thing to be positive definite. This guy's positive definite as expected because it's a quadratic bowl that I just made up, right? So it is by definition positive definite, but the Hessian of the Lagrangian, which includes that constraint curvature term, is now indefinite. Ooh, badness. Okay, so that's what's breaking this right now. We're actually getting into a place where the constraint curvature term that's in the Lagrangian is actually indefinite and is messing us up and is making our Hessian indefinite. So takeaway message from this is you still have to regularize. And in fact, here the objective is benign, right? The objective is convex, but the constraint is not convex. And the constraint term, curvature term, is messing us up. Okay, that's fun.
So it's like
Well, the function f might still be non-convex and bad. But in this case, I have a convex f. So, okay, so that's why it broke. So what do we think about Gauss-Newton? Now I'll just do Gauss-Newton and I'll throw out that constraint curvature term. What do we think is going to happen here? If I start at the same spot. Let's try it. I mean, yeah. So we'll try the exact same thing, exact same starting spot. And let's see what happens. So this guy goes kind of down that same area, but it keeps trucking. It overshot a little bit. We fixed that with a line search. It ended up making it to the optimum. So in this particular problem, it turns out that constraint curvature term totally screwed us up, made the Hessian indefinite and caused these kind of problems. So obviously regularization is kind of the general answer here. But kind of a meta point is that that if you're regularizing this thing, you're kind of messing with the Hessian anyway. So that constraint curvature term, if it's negative, like you're basically going to regularize it out anyway. So if you're regularizing, that term's not really doing anything good for you. It's kind of the meta point. It definitely helps that the tail convergence when you're close to the optimum and everything's on the rails and doing well, cool. But if you're far away and you're doing regularization, it's not really helping. It's kind of the meta point. It can make things worse is also. Yeah, pretty much. And that's often the case in control problems. Like we make up the cost function, right? So usually if we're being reasonable, we'll make up a nice benign like quadratic or convex cost function. So F's usually nice because we get to pick it. But the constraints we don't get to pick, right? They're usually the dynamics, the physics, safety. So those things are usually things we're stuck with. So often the costs are nice and the constraints are the nasty part. And so in that case, that constraint curvature term can be bad and mess with you. So that's kind of another reason why we often use Gauss-Newton in control stuff. Okay, any other questions about this? Yeah. So there's a little bit more to say about this, but basically indefinite Hessian bad, right? Like we saw before, that corresponds to like something non-convex going on, and it means we have to regularize, and we didn't regularize. So it ended up messing us up. This is a little subtle. We're going to get to this in more detail. Anybody else before we move on? Yeah.
You regularize exactly the same we did before. You just like
No, which is why we got more to say about this. So give me some time. We'll get there. I just want to give you a heads up that there's some demons lurking, right? And we need a little bit more. Okay, so we did this nice example. You have the code. You can try it yourself and mess around a little bit. But I just want to say, right, if we start at, so the first time we started at like -1, -1, if you want to go back. And then we tried this other point that was a little farther away, and we got full Newton got stuck. And we didn't put any guardrails on, right? We didn't do the regularization. We didn't do the line search. So back to like, you need those things to have the thing work. Kind of the message here is you still have to do those things. And there's some slight tweaks we have to make to how you implement them in this case that we're going to get to now. But in that case, right, the issue is an indefinite Hessian coming from the constraint curvature term. So the fix here is to do regularization. But it so happens because F was benign and convex, the Gauss-Newton worked fine. And that's kind of a meta takeaway there about like, the relative benefits of these things. And often that extra term isn't buying you a whole lot of performance. Okay, so that's that. So some takeaways then from this. You may still need to regularize. The Hessian of the Lagrangian, right? Even if the Hessian of the objective is convex. And that's because of the constraints. And then, yeah, I kind of just told you this, but we'll see more of this. Gauss-Newton is really common in practice. And back to like people being a little bit lazy with, conventions and naming and notation. Often people will say they're doing Newton's method when they're really doing Gauss-Newton, and kind of there's a bunch of overloading and stuff like that. Okay, any questions about this stuff before we keep trucking? We got like 10 minutes. So what I'm going to do now is, we're going to circle back on like kind of how to do regularization and line searchy stuff in the constraint setting, probably next time. I'm going to do that after we do inequality constraints. We'll do it all together. So what we're going to do now is kind of start talking about inequality constraints, but we're probably not going to get to finish it today. All right, so to make life a little easier, we're only going to talk about inequalities right now. And then like putting together is no big deal. You basically put both sets of techniques together and stack up and life is good. So we'll just handle for now a single inequality, basically just the inequality version of what we just did for the equality case. So we're going to have this C of X positive now. So greater than or equal to 0 instead of equal to 0. And we're going to try looking at the exact same picture. So as a note, we'll just consider inequalities for now. And basically, you just combine the things. And as we said, right, generally for us doing control stuff, equalities are usually dynamics constraints. They can also be something like a goal constraint, like you have to get to this state at the end of the trajectory horizon or something like that. They can be that. Inequalities are usually things like torque limits, actuator limits, thrust limits, stuff like that, right? On your controls. And they can also often show up as safety constraints, like keep outs. So usually we have inequalities on the controls to basically reflect actuator limitations. And then we often have inequalities on the states for safety stuff, keep out of, don't hit stuff, that kind of thing. Okay, so let's do this. So the kind of the basic message is the first order necessary conditions here. Again, there's some math gymnastics that we're going to have to go through, similar to before, with a little bit more complicated. But the intuitive statement in words is exactly the same. So number one is we need the gradient of the objective to equal 0 in the free directions. And then we need the constraint to be satisfied, which in this case means C of X greater than or equal to 0. So that's it. But there's some extra stuff that we're going to need to sort of pile on to get there here. So maybe let me draw the picture again. Maybe I can just copy this one. That would be great. Is this going to work? That would be super convenient. Okay. Ah, damn it. Okay, cool. So now we have to think, before I mention, the interpretation here, and C is positive on the left and negative on the right, crosses 0 along the line. Now the signs are important. Okay, so remember C, we want C to be greater than or equal to 0. So in this picture, I don't have to be on the line. Where do I have to be? Up and to the left, right? I can be anywhere in that upper left region. I don't have to be exactly on the line. And right, if I flip the sign and, went the other way, I'd be in the lower right, whatever, right? So that's kind of the idea. So we need to be up here somewhere. This is all the good stuff. And I sort of almost drew those parallel to correspond to level sets, which would have been cool, but close enough. So this we call over here the feasible region, or feasible set, or whatever. where the constraints are satisfied. Okay, so I think what I'm going to do, and we'll probably revisit this next time, but I'll like state the first order necessary conditions, and we'll talk through and like interpret them a little bit. So let me just write them down. They're going to be familiar looking, but there's some extra stuff. Okay, so first we have a gradient condition that's really, really similar to what we had before, with one minor tweak that we'll have to talk about. Okay, so we got this guy, looks very similar to before. Then we've got the constraint being satisfied, same as before, but now it's an inequality instead of an equality. And now we got some extra stuff. So before we had a Lagrange multiplier, just like this, but now we care about the sign of the Lagrange multiplier. So before it could be anything. Now we're going to also require that lambda is, oh, I messed the sign up here. Everything's positive. And then we're also going to have this final condition, which is going to look a little weird, that I'll write out a couple ways. So we need lambda times c, and I'll write this two different ways, and we'll talk about it, to equal 0. Okay, so each one of these lines has a name. So I'm going to give you the names real quick. And these are the famous KKT conditions. Who's seen these before? Just curious, show hands. Like not too many, but a few. Okay, so these are called KKT conditions. And just, we're basically out of time today. So I'll tell you what these names are, and then we'll talk through them more next time. This first one, which is gradient equals 0, this is called stationarity. This next one that says the constraints have to be satisfied or feasible is called primal feasibility. And primal, remember, refers to the x, right? And dual refers to the lambdas. This is called primal feasibility. Basically means that the x's obey the constraints, right? They're feasible. This one, which is an inequality constraint on the lambdas, sort of obviously it's a constraint on the duals. It's called dual feasibility. And then this last one is called complementarity or complementary slackness or kind of whatever. And this actually encodes switching behavior. So roughly speaking, what's going to happen here is I've got two options as far as the constraints are concerned. If I'm in that feasible region in the interior somewhere, like if the minimizer were actually, if the unconstrained minimizer were in the feasible region, then I would just go there. And essentially then this Lagrange multiplier term shouldn't be there, right? In which case the constraint, the constraint's strictly greater than or equal to 0. So in that case, for the stationarity condition, I want the constraint to drop out, and I want lambda to be 0, basically, right? In the interior, it looks like an unconstrained problem, and therefore I want lambda to be 0, and I want the constraint term to drop out. The other option is that's called an inactive constraint. If the constraint's active, which means we're on the boundary, then it looks like an equality constraint problem, and I need the Lagrange multiplier term. So that switching of the constraint on or off to look like either an unconstrained problem or an equality constraint problem, that's handled by this complementarity. So what this is saying is if the constraint is greater than or equal to 0, like it's satisfied, then for this to work, lambda is 0, right, in this product. If the constraint is equal to 0, once I'm on the boundary, lambda has to be, then this has 0 and lambda can be non-0. So that encodes this on-off switching. Does that make sense? Yeah.
One of them has to be 0.
Exactly. It makes one or the other be 0, such that you're switching, you're basically either inactive constraint where lambda 0 and that it drops out of the stationarity condition, or it's on the boundary, it's active, C0, now lambda is non-0, and the constraint term shows up in the stationarity. Okay, and that's basically it for today. So we will pick up right here next time.